Look at this breakdown of planetary mass in our solar system. Stripping away the sun, the remaining material is almost entirely monopolized by a single object. Jupiter accounts for over 71% of all planetary mass. Everything else, Earth, Mars, the ice giants, is leftover debris. The physical dimensions of that mass are hard to conceptualize. You could fit more than 1,300 Earths inside its volume. Yet despite its immense bulk, it completes a full rotation in under 10 hours, spinning so fast that its equator noticeably bulges. That composition, mostly hydrogen and helium, closely mirrors the sun. If the protoplanetary disk had fed Jupiter roughly 80 times more mass during its formation, the internal pressure would have triggered thermonuclear ignition. We would be living in a binary star system. Because of that immense star-like gravity, Jupiter became the physical anchor of our planetary neighborhood. To piece together how Earth formed and remains stable today, we have to look directly at the physics of the gas giant next door. For decades, the standard textbook model of Jupiter was fairly straightforward. Scientists assumed that deep beneath the clouds lay a clearly defined, solid rocky core, roughly 10 times Earth's mass, neatly wrapped in layers of gas. In 2016, NASA's Juno spacecraft entered orbit to test that assumption. By tracking minute changes in velocity, tiny Doppler shifts caused by variations in Jupiter's gravitational pull, researchers finally mapped the interior structure beneath the opaque clouds. The readings contradicted the old model. Instead of a solid center, Jupiter possesses a fuzzy interior where heavy elements are mixed into the gas in a state of matter never before observed on a planetary scale. To grasp how Jupiter actually governs the solar system, we must move past old assumptions and journey into its chaotic alien depths. This diagram illustrates what planetary scientists now call a dilute or fuzzy core. Instead of a sharp boundary separating rock from gas, the center of the planet is a massive, messy transition zone. Heavy elements like rock and ice are blended directly into the surrounding hydrogen, stretching out to nearly half of the planet's total radius. As you move outward from that soupy center into the surrounding envelope, the environment reaches an extreme threshold. Here, the internal pressure exceeds 2 million atmospheres, and temperatures soar past 10,000 Kelvin. Under that crushing weight, hydrogen undergoes a phase transition. The pressure is so intense that electrons are squeezed off their parent protons. The hydrogen stops acting like a gas and becomes liquid metallic hydrogen, a fluid that conducts electricity with the efficiency of a metal. Since Jupiter rotates every 10 hours, this massive ocean of electrically conductive fluid is constantly churning. The swirling kinetic energy creates powerful, continuous electric currents deep within the planet. Those deep internal currents act as a planetary dynamo. They are the sole engine pumping out the most massive and powerful magnetic field of any planet in our solar system. That intense internal heat eventually rises, driving the weather we see. Those iconic colorful bands decorating the surface are alternating jet streams blasting at 400 miles per hour, grinding against each other. Juno's data proved they aren't superficial. These winds penetrate 3,000 kilometers down into the atmosphere. Caught between those opposing atmospheric belts is the Great Red Spot. It is a high-pressure anticyclone that astronomers have observed for nearly 2 centuries. Just like the jet streams, the roots of this storm extend hundreds of kilometers straight down into the dark. But the storm is changing. Recent tracking from the Hubble Space Telescope shows that the Great Red Spot is currently shrinking. Its waistline is reducing by roughly 580 miles a year, and the outer edges are visibly flaking apart, shedding fragments of red cloud into the surrounding atmosphere. The turbulent surface of Jupiter acts as the deep, violent exhaust of a massive planetary heat engine. That engine's influence extends far beyond the visible clouds. The magnetic field we mentioned earlier forms a massive, invisible bubble around the planet, with a magnetotail that stretches so far it occasionally reaches the orbit of Saturn. As this 3D map illustrates, the asymmetrical magnetic field lines interact with the solar wind, trapping high-energy particles in a toroidal or donut-shaped radiation belt. The electron and ion flux in this zone is 20,000 times more intense than the radiation belts surrounding Earth. Orbiting directly within this lethal high-radiation zone are the 4 Galilean moons. The innermost moon, Io, is locked in a gravitational tug-of-war with Jupiter. The resulting tidal friction literally flexes its rocky surface by up to 100 meters, melting its interior and making it the most volcanically active body in the solar system. Further out, that same tidal heating has a much different effect. Beneath the thick, icy crusts of Europa and Ganymede, the friction sustains massive, liquid saltwater oceans. Europa alone likely holds twice the liquid water found on Earth, protected from the harsh radiation above. The interplay of Jupiter's immense gravity and radiation creates a dynamic, miniature solar system. These conditions force a re-evaluation of the habitable zone, proving that liquid water, and potentially the chemistry for life, can exist deep within icy satellites, far from the Sun. Looking at this model of the early solar system, you're seeing the grand tack hypothesis in action. Jupiter didn't form in its current position. It coalesced closer to the Sun and migrated inward to roughly the current orbit of Mars. As it moved, its massive gravity acted like a cosmic snowplow, scattering planetesimals and clearing the inner solar system of debris. This inward journey depleted the material available for Mars to grow, locking it in as a relatively small planet, and mixed rocky and icy bodies together to form our modern asteroid belt. The migration was only halted when a newly formed Saturn exerted enough gravitational torque to pull Jupiter back out to its current position. Today, Jupiter's gravity continues to sculpt that asteroid belt. Through mean motion resonances, specific orbital points where Jupiter gives asteroids a regular gravitational tug, the planet literally ejects material, carving out completely empty stretches known as the Kirkwood gaps. That massive gravitational reach led to the Jupiter shield theory. The idea is that Jupiter protects the inner planets by vacuuming up comets that might otherwise hit Earth. The dark, bruised impact scars left by comet Shoemaker-Levy 9 in 1994 provided clear evidence of the gas giant absorbing a catastrophic hit. However, modern orbital simulations suggest Jupiter plays a dual role. Sometimes it acts as a sniper. Its gravity frequently perturbs icy bodies from the outer solar system, captures them, and then flings them directly onto Earth-crossing orbits. While that sounds terrifying now, in the early days of the solar system, this violent bombardment was beneficial. By redirecting water-rich planetesimals toward the Sun, Jupiter's sniper behavior likely seeded a young Earth with the oceans necessary to spark life. Our understanding of Jupiter now extends beyond our own solar system. Migration theories like the Grand Tack provide the mathematical framework to explain how hot Jupiters, massive gas giants orbiting dangerously close to distant stars, reached their scorched positions. Today, observatories use Jupiter's atmospheric data as a template to understand the chaotic global dust storms of super-Jupiters. By comparing the two, researchers can decode the chemistry of distant atmospheres. And statistically, gas giants accompanied by ocean-harboring icy moons are incredibly common. They vastly outnumber Earth-like rocky planets, orbiting in a star's traditional habitable zone. Jupiter's gravitational governance provided the cradle for Earth's evolution. As we continue looking out into the galaxy, this giant remains the universal measuring stick we use to gauge the nature of worlds across the cosmos.